We have a good evening planned for you all tonight. Of course, our main is our guest speaker this evening, and he was an astronaut on 1997 mission to the ISS on the space shuttle, and I think you'd all like to give him a big welcome. I'd like you to welcome Bjarni Tryggvason.
So we were just having a conversation with some folks here about kind of what this talk is all about. I've been pretty lucky in my career. I escaped out of university back in 1972, took engineering physics at UBC, and I'm a UBC fellow grad here, escaped out of physics. And then, I've been pretty lucky in my whole career kind of thing. I went from there to work at the Atmospheric Environment Service in Toronto, doing atmospheric physics. And from there I went to University of Western Ontario at the Laurier Wind Tunnel Lab, where I was doing aerodynamics of buildings and things. And before I went to university, I'm not sure I can show it much louder, but before I went to university, I learned to fly. I became a pilot right after grade 12. And so my interest was always kind of in the flying side of things. Because the jobs I tended to, and actually when I went to university, my goal was to become an Air Canada pilot. But I ran into a lot of interesting things at university, and I decided, no, I'm going to stick with research and development kind of stuff for my career. Flying is my hobby, and it still is that way, but I've got lots of flying experience. You know, so when I went to university, I was studying physics and math. And my curiosity, or the question I had in my head when I went was, does this physics and math really work? And particularly, does the math really work for the stuff that we do in our lives? And it does. And I eventually learned that. It took a while, but it does. This thing I'm going to talk about now is we're doing some experiments. We're running a bunch of essentially educational type experiments on the space station. And the driver behind it is the poor quality that schools are doing in North America, particularly in the States, but in Canada too, in STEM education. Science, technology, engineering, and math. And so this little group here, which is basically that's the motivator for these things. And the program is called Story Time from Space. And you can Google Story Time from Space, and you'll see all sorts of stuff about this project. And then we have some support from this Jeff Bennett. He's got this big kid science. Jeff Bennett is a astronomer, and he makes his living really writing textbooks, physics textbooks for university level. And they write some kids' books and a few other books as well. And then CASES, which is the Center for Advancement of Science in Space. So that's a NASA-supported group that's in Florida, and it manages half of the U.S. labs on the space station. And so we get all our stuff up to space through CASES and through NASA. The driver is trying to put together stuff that will help increase the quality of education in the STEM subjects in the school system. And our focus is primarily the U.S. schools, but it can work in Canada too. And it's the U.S. schools because even though all the work is done in Canada, and all our support comes from NASA, so we're directed at those schools, but we have the same problems here. Here's a picture of the space station. You've all probably seen this. The lab facilities are these things here. The U.S. labs, the Russian labs, Japanese labs, European lab, and the robotic systems here is what Canada contributed. And for that, all the partners get to use the space station. There's actually two space stations up there. They're bolted together. There's the Russian space station and the International Space Station.
Are you allowed to move wherever you want, or you need permission to go from one station to another? Passport?
There was some silliness partway along the way, early in the program, as you gotta stay on your side and we stay on our side. That silliness went away. But all the Russian work is done in this segment here. And all the stuff, US, Canada, Europe and stuff, is done in these segments here. So the work is split. There's a border there. The control of the whole space station is shared by Moscow Control Center and the Control Center in Houston. The Russian part actually does the majority of orbital control on the whole space station. The American part, which is sitting here someplace, controls the attitude of the space station. It works out pretty well, in spite of all the political antagonism that goes back and forth some other ways. Just to give you an idea of the size of this, and here's the space shuttle. And space shuttle, about the size of a very famous airplane, the 737. It doesn't have the same problems that the 737 MAX has, but just to give you an idea, so this is the size of like the WestJet airplanes that fly into Kitchener-Waterloo. So just kind of keep that in mind. And the space station is pretty big. It's got the size of a football field, and it's got 500,000 kilograms. The Canadian part was the robotics. So we built these robotic arms for the space station. We had done the same for the space shuttle. And it's because of that contribution, basically developed the arm for the space shuttle, that NASA invited Canadians to fly on the space shuttle. Space station, Canada developed that arm. How much would you pay for a robotic arm like that?
How many million?
Yeah, how many millions?
1 billion?
Closer. $2 billion. Yeah.
Does that include transportation?
And then for the $2 billion, you get the privilege of paying about $30 million a year to support it and fix it, whatever else comes along. It's your toy, so it's your responsibility. Yeah, so Canada spent a lot of money on this, and very little on doing science in the space station, which was, I thought, the whole point of the space station. Yeah, a little bit of politics. So you've seen pictures of the astronauts floating around. So why do astronauts float? They're weightless? What does that mean?
They're away from the gravitational pull of the Earth.
They're away from the gravitational pull of the Earth?
They are falling all the
They're
time.
falling as fast as they're going around the Earth, so they just stay in the same spot. They're going
This is a physics guy.
Yeah.
Not to embarrass anybody, but there's a lot of funny conceptions about why astronauts seem to float inside their spacecraft. Right? None of those answers are right, by the way. What's the difference between weight and mass? Physics.
Put it into words, but
So weight is the force of gravity, and mass is something else.
it's the
Anybody else?
Weight plus volume.
Amount of matter.
Which is the amount of matter?
Mass is the amount of matter.
So amount of matter. Does it have something to do with volume?
That'd be dark matter?
Sorry?
No, nothing.
You're afraid, okay?
No, I said dark matter?
Dark matter. That's even more mysterious. Anyway, so, will a balance work in space? What's the difference between a balance and a scale? Does balance won't work in space? Needs gravity to work? He's another scientist, and yeah, he raised chickens most of the time, but he was an engineer. He did what, physics to start with? And then chemistry, and then electronics. So you see, there is, how does one say it? Lack of clear thought. Not being miserable or crappy at you or whatever, but confusion for sure. Okay. And the space flight make astronauts taller, I guess.
Yes, temporarily.
Do they get shorter just as they're going into space?
There's no force acting on the person, so I guess generally it would stretch until we get back on Earth, and then where the gravity is mostly what's pulling it down.
So what's your answer to that question then?
Oh, then yes, they get, I think they would get slightly longer.
But you explained it the other way around.
When they come back.
While they're in space, they're
You
taller.
suggested they get shorter when they come back.
Oh, I guess I'm wrong.
They grow a half-inch taller because no compression.
Yeah, so, okay. So without compression, you stretch out. But it wasn't space. Being in space stopped stuff that's happening to you here on the ground, not did something new to you. So these are all common misconceptions that people have. And you know the guys that have the best fine-tuned version of this common misconception? They're astronauts. Okay?
Like you.
Like me. Except I'm an oddball astronaut. And actually there's a lot of people, you'll hear people that run NASA, high up in NASA, they give you all sorts of nonsense about these ideas or these concepts. They're poorly explained, they're poorly understood, and that poorly understood stuff is just repeated again and again and again. Because I guarantee you, you see astronauts talking about this in space, 9 out of 10 are going to say, I'm weightless because there is
No gravity.
no gravity in space. So I've had physicists tell me that. Yeah. And then they say, well, what was that Newton's law of gravitation tell you? Does that ring a bell to anybody?
Yeah, but it's been a really long time.
How does the space shuttle or space station stay in orbit if there's no gravity in space?
It doesn't. It's falling all the time.
But it's staying in orbit because it's moving fast enough to counteract the force of gravity. Well, it's not counteracting it, but it's keeping balance.
Compensating?
So, the point of all these little experiments we're doing is to draw out these ideas. And when we pitched this to NASA back about 4 years ago, to a room full of engineers whose whole job it is to look at stuff that people are proposing to do on the space station and decide, does it make sense? Do we waste our time letting them do this, et cetera, et cetera? I stumped all of them too. So they got quicker on to understanding what's going on here. And so they like the experiments and say, yeah, we'll give you the time to do this. And in fact, we have, the little group I work with, we have a very unique contract with NASA. Anytime I come up with an experiment I want to fly, I just say I want to fly it in April of next year. They put me on. I don't even tell them what I'm doing. They will eventually learn. But they like the stuff we're doing because it really draws out these ideas to try to clarify what the heck is going on in the science. And there's a lot of problems with science education in North America. These whole experiments are kind of sent to look at that. So it's just an educational program looking at STEM and literacy. We apply some essentially storybooks in space. Astronauts read those, and you can go to the website and you can see all that. And the storybooks typically, we look for books that have a connection to science. And then we do educational experiments to complement some of the ideas that might be covered in the books. So you can go to, like I say, you can go to the website and you can see some of this stuff. My part in this, I develop all the little science experiments. And they're demonstration experiments. We're not doing science or anything like that. Anyway, so you can go to this website here, and you can see a lot of this stuff. And it's intended to be used by educators and anybody else involved in education. And the first 5 books we wrote were written by Jeff Bennett. He's an astronomer. And they were clearly connecting, it's a storybook about stuff going on in space, but connected to some of the science ideas or concepts that are behind this. So here's a picture of one of the astronauts in the cupola, part of the space station. These are Jeff's books. Is to engage educators in looking at these ideas and to get the ideas correct. Do it in ways that may be fun. Maybe this little stuff we did was fun. Maybe it wasn't. Maybe it's a little bit of funny torture instead of fun dialogue. But it is to do these things, and I don't remember all of what's on the slides I've got here. So anyway, so these are the people that are involved in this. Patricia is the character that started it. She used to be the director of education at the Space Center Houston for about 10 or 15 years. She lives in Penticton now. Myself, I develop all the science experiments. Jeff Bennett is an astronomer, a teacher, and some other folks here. Here's a picture of me on the space shuttle doing the kind of science I was doing up there. So we've had a bunch of stuff line up to, actually this one's a little bit out of date here. Anyway, we sent experiments up there, sent books up there, and we have this agreement from now until 2024, I can conjure up stuff. Tell them what flight I want, up I go. Up my experiments go. I wish I could go with them, but they're not that nice to me. So. And actually these other ones, hardware, this actually flew up just a couple of weeks ago, and some of these other books went up. So about a year from now, we'll have another set of experiments. And one of the things I want to do is involve some university types in helping develop some of these experiments. And the experiments deal with basic ideas that are dealt with in the school systems. So we're looking at energy stuff, heat transfer. And one of the things that we're doing here is, like, there's an energy balance of the Earth. And the Earth, from an energy point of view, sits between a really hot sun and really cold space. When the sun radiates energy to the Earth, and how much energy it absorbs depends on how well it absorbs that energy, which depends on what's in our atmosphere, how much cloud cover, how much ice cover, and what's the surface like. And how much it radiates out to space also depends on those things, but in a different way. And if you upset the properties of the Earth that affect this, then you change the temperature of the Earth. And this is a big debate, climate change and global warming. And what percentage of people believe that's not happening? There's a lot. Some of them are presidents of the United States. Some of them were our last prime minister. And they say, I don't believe this stuff. And what Harper did was, he fired all of the scientists working for Meteorological Service Canada who were dealing with these issues, so no scientist in government could contradict it. That's what Harper did. Trump hasn't done that yet.
Every time.
Yeah.
But like this is an incredibly simple problem dealing with just heat transfer. So we're doing experiments that do that, and then we tie it back into some of these big issues. Science in a free fall environment. What is free fall? What is this weightlessness business? So what we do is, and I don't remember what all my slides look like, so I'm so these are the set of experiments, and these are all things that you run into in high school, like meniscus and buoyancy and different colors of light, and how balances work, and so on. So we can do things in the free fall environment that are similar or the same as what you might do on the ground. And do you always see different things in space than on the ground? Or do you sometimes see exactly the same? And yet you're still in a free fall environment. And how do you put that together so you essentially push people to clarify the ideas and clarify their thinking on it? So that's kind of what the experiments do. And they're not complicated, they're really simple. So, yeah, so we compare behavior in the ground and in the free fall environment of space. Under what conditions are they the same, and what conditions do they appear different? And what do we learn about sort of the science concepts in doing that? So we're going to see some of the experiments that we've done. So the energy transfer, the sun transmits its energy to the Earth through radiation. That's pretty amazing, I think. Like it's 90 million or 100 million miles away, 150 million kilometers or something. And that energy comes all that way and gets to us. Pretty amazing, I think. Some of it's absorbed, and so we did an experiment where we were looking at what affects the absorption of the energy coming from the sun to us. And so the Earth's temperature depends on how it's received and how it's absorbed. Then that's not enough. There has to be another part to that experiment, which sometimes people forget. It's not just coming in, it's also leaving. It radiates out to space. What's the temperature of space?
Pretty close to zero.
Pretty close to zero.
0.7.
Yeah, it's about 3 or 4 degrees Kelvin on average or something like that. So that's like minus 270 degrees centigrade. So space is a big absorber of energy. And the Earth is in between the hot sun and the space, and there has to be a balance that ends up doing it. If you, like I said before, if you upset that balance, then you change temperature. So we flew these little discs, and these are not complicated. This is stuff that all of us run into, and we see it happening. Like if you walk on black pavement on a sunny day in Bear Creek, it's kind of hot. You know, better to walk on the grass or something light. You know, so we expose these to the sun's radiation through a window on a space station, and we see how the temperature of this rises. And it rises, and we know how the temperature rises. What kind of equation we describe that?
NC delta. Is that the changing of temperature of a certain object?
Yeah, but like there's a really simple equation that describes it. It's an exponential change, and it's so simple. Can you run into that in probably grade 11 or 12 or something? Does it work? Like is it physics when you study in school, does it really describe how stuff really works? Okay? And it's not always easy to show that. And part of the thing is, like I have met very few people, like I teach at the university level, and in engineering, and I meet very few students in fourth year engineering who connect the math to the world. And I was teaching a course in space systems design at the university, one of the universities in Iceland, and I've taught it here at Western as well. And my course is applying all the stuff to design stuff that's going to work in space. The comment I got from the students was they'd never thought or understood or saw how the math they were taking at their university level or they took in high school, how that had anything to do with anything else that they're doing, even in engineering. Even as they're using some of this stuff. And that's a very common thing, you know, even at that level. And in the school system, there's very few teachers have any idea what the hell I do with all this math stuff. There's no connection between teaching arithmetic and science, or math and science. And you can jump on me here if you
No?
disagree. Yeah. Because most of the teachers have no idea what guys like me do to this stuff. So they can't give a connection to their kids. That the arithmetic you're learning and the math you're learning actually describes how the world works. Anybody comment on that, or?
That's about right.
Yeah, about right, yeah. So like in this example, we don't just measure the temperature, we actually measure how it increases over the 10 minutes of class. And that increase with time is actually modeled really well with a simple exponential thing. And so we want to show that this simple equation is what just describes this line width accuracy. Now you may have to do the experiment just a little carefully. And you're always dealing in this thing here. So this is in the window of the cupola. The sun is shining on it. But again, there's a balance. The sun is heating it up, but the energy coming in is now being transmitted to the air in the spacecraft and distributed. And that gives you, eventually you just reach a steady state temperature in this experiment. You can do the same experiment on the ground. And since it illustrates, yeah. So that's the heat transfer part. So we do this in space, where we get lots of people interested in looking, and then you can do them on the ground. You see exactly the same things. To try to tie that it's the math that describes this stuff, and it describes it really, really well. So the other thing we're doing, looking at the energy balance on the Earth. All the energy comes through the light coming from the sun to the Earth, and the Earth absorbs some of that. And some of it gets attenuated by, like it's really amazing. Don't worry about reading all this stuff. In our atmosphere, we have CO2. People have heard about CO2?
Carbon dioxide.
What's going on with CO2 in the atmosphere?
It's increasing.
Talk loud.
Oh, it's a greenhouse gas. So
It's a greenhouse gas, yes.
that increases
In
traffic. So like
Yeah.
traffic-
So let's say it's a greenhouse gas, but what's happening to CO2 in the atmosphere?
It's reducing the amount of energy coming to Earth.
It's the percentage is increasing.
It's increasing.
It's increasing.
We burn fuel.
Yeah. The
Increasing.
amount of CO2 in the atmosphere is increasing. So whatever it does is changing. Right? Now CO2, it's a greenhouse gas. CH4. How many chickens did you raise? How much CH4 did they produce?
Considerably. The cows more.
But cows do more. And H2O, water. The dominant greenhouse gas in the atmosphere is water. 65%. CO2 is 1/10 of that. So why the heck do we care about CO2?
It's more effective to transport energy.
No. The water is what does it, okay? The CO2 does a little bit. And if you increase the temperature of the air by 10 degrees, you double the water it can hold. So CO2 is a little wiggly thing, and it drives the water vapor up and down by a huge amount. And that drives the temperature of the atmosphere. Okay? So what does that have to do with light and stuff? Okay? Well, the light that we get from the sun is different colors and things. And we flew a spectrometer. The light comes in this end over here. It's kind of It's kind of like a funny little telescope, right? Yeah. Light comes in one end, there's a camera on the other end, but in the middle is a grating, and it breaks the light into the different colors. Okay? So in one direction it's the field of view, and the other direction is different colors of light. Okay? So we flew this thing here, and you can see how big it is. And this is actually provided by a company here in Waterloo, PMP Optica. What we were trying to do, so here's a data from this thing here. This is from a light bulb. So you see here's all the colors or wavelengths of light. This axis here is wavelength. And so from a light bulb like one of these guys here, it would give just these bunch of specific lines for specific colors. So what we're doing is we have the astronauts aim this thing at the sun when there's nothing between him except this window and the sun. So we measure the spectrum of light from the sun. And then as the space station goes through a sunset, you start looking at it through more and more atmosphere. And the atmosphere absorbs some of the light. And it absorbs light by what in the atmosphere absorbs light? Just based on this discussion we just had.
Greenhouse.
The greenhouse gases. And the biggest one is?
Water.
Water. So the water absorbs some of the light. The carbon dioxide does. The methane does. And a bunch of other things do. So where you see these spikes, this is where water or carbon dioxide or something absorbs the light. So we're going to point this at the sun, and as you go through the sunset, you start looking at more and more atmosphere. And so the light is attenuated, but it's attenuated more at the frequencies that are absorbed by water vapor, carbon dioxide, or so on. Now you can do this experiment on the ground as well. And so you can do this in space where we have a clean shot of the sun. From the ground, you never have a clean shot of the sun. You're always looking through the atmosphere. So, now the political complaint. Canadian scientists were the first ones to invent major instruments to measure this from the ground. It's called a Brewster spectrometer. They were all fired by Hartman. Canadian scientists, some of them are my friends, were the ones to find the ozone problems using the Brewster spectrometers invented in Canada. All of those scientists that were doing that work were fired by Hartman.
There's a company in Montreal who's going to put up methane detection satellite. Was that part of that? Is that helping with that group of work that was done? Is that
No, that's probably ABB.
No, it's maybe, but it's a separate name.
Yeah, if they're putting it into space,
Yeah.
that's supported by the Canadian Space Agency.
Okay.
But it's ironic, like the guys that invented this, because on the ground, cut by Harper's gang, because he doesn't believe in global warming or people's effect on the atmosphere. Yeah, so this one here, we tried to do this experiment, and here I'm gonna stick in another little bit with some videos now and again. I may skip some of these because so this is one of the astronauts. This is on the space station. We're looking out the windows of the cupola, which is which are the main windows in the space station. And here you see the spectrometer. And he's pointing it someplace. Oh crap, on windows here.
I was going to say, yeah.
Does that not affect the,
It will not affect the spectrum. It'll mess up if you're trying to take image of it, then you get diffraction around all these things, so it's gonna mess up your image of stars, but it's not gonna mess up the spectrum, because on that one axis, it's a spectrum of light, so that will not shift. Anyhow, so he's poking this thing out there, and we got the data down for astronauts. We got the data down, and I told my NASA buddies he didn't do the experiment correctly. What would you think their response is to that? Astronauts are not allowed to be known to make mistakes. So I said, nope, your hardware must have messed up. And they said, no, my hardware couldn't have messed up because I actually got a spectrum. It's just nothing like what we're expecting. Well, maybe you're expecting the wrong spectrum. No, the sun spectrum is really well known. So, anyhow, so there's no point in arguing.
So you have to go up there and do it yourself.
That would be a good fix. Anyhow, I don't know what he was pointing at. It was not the sun. And he had to be watching his little computer screen, and we needed to see a bright line across the screen. And that's what the instructions were. And this guy didn't read the instructions very well. You know, so we got no data at all. So we are going to apply it again. But I'm going to bypass the astronaut. So we want to design a little thing that will actually point it automatically at the sun and track it, like your telescopes, you know.
If you need any help with that,
Because
you
it's,
know.
I guess a really neat experiment, and it can show how all of this stuff that people talk about in this greenhouse gases and stuff actually works. Buoyancy. So what the heck is buoyancy? Buoyancy is sedimentation. It's simple, not a trick question.
You float in water.
Yeah, buoyancy stuff floats, and sedimentation sinks. Okay? Why does it do that?
It's heavier.
Density.
Density?
Gravity.
Okay, density is part of the answer. Say again? An accelerated
Gravity.
Accelerating force.
yeah, accelerating
Gravity
force.
shield or motion.
That's good. You can almost get rid of the force. If you hit acceleration, that causes a pressure gradient in the fluid, then the density separates out. Anyhow, so in space, what's going to happen? Will we see buoyancy and sedimentation in space, where we have free fall? I'm glad you said that. I said to me, so hang on, something to do with acceleration, right? So if we're in space, and the experiment has a little chunk of water captured in a little vessel, styrofoam balls, and steel ball bearings. So what are they going to do in the free fall environment of space?
Sit there.
Sit there? What does that mean, sit there?
If they're in the middle, they'll stay in the middle. If they're in the top, they'll stay at the top. They're
Okay,
bottom.
that I understood. I didn't understand, sit there. So they're just gonna, wherever they happen to be in the water, they're gonna stay there. So I'm gonna come back to ask an acceleration question. Anyway, so we had this little vessel, a little hero cab right here, standing on this little stand, and we could rotate it around. And we can skip all this stuff here. So here, there's a picture of the vessel, and this is taken on the ground. Steel balls on the bottom. Foam balls on the top. Then we had a little stand, so we bolt this to the end of this thing here, and it can rotate around that little center stand. And here's our astronaut. doing this. And when they're doing this, we ask to have live downlink so we can kind of be looking over their shoulder as they're doing it, just to make sure. And this guy put this on incorrectly, you understand. It would never work this way. Well, it actually would, but it's not the way we're trying to do it. You know, so luckily I can just call the guy in Florida. Actually, I'm on the Skype, and I say, hey, he's got this mounted incorrectly. Can you correct him? And it goes up there, and the guys explain it to him. And I hear all this stuff, so we got him to fix it. That's a picture inside the space station, all this stuff around here.
Messy housekeepers.
Yeah, the messy housekeepers. So, another little pause here. So here the guy's got it oriented the right way. We're going to go to 4.5 minutes. I'm going to try to ignore him. So here he's got it set. And he kind of, and then he spins it around. So now what's this thing doing? It's accelerating. Anything going around the circle is accelerating towards the center of the circle.
It's centrifugal force. Centrifugal force.
Which kind?
Centrifugal.
Centrifugal.
Centripetal.
Central. You got centrifugal, and you got centrifugal.
Yeah.
Going once. How many for centrifugal? How many for centripetal?
Oh, yes. Sorry.
Centripetal force. Okay, so you see what happens in the experiment? And what do you suppose those things are going to do when that's happening?
But shouldn't that one slow down because it's in microgravity, not gravity?
That's another good question. Microgravity versus gravity.
How about friction?
Friction, another good question. Yeah, so here we have our Hero 2 thing. I'm going to go to.
We're about to get seasick. You're going to stay put.
He's going to give it a push. It's going to run around the circle. You see that floating in the middle?
Because they've been given inertia.
Just a second. Backward. Find the right spot here, I'm not sure why. What are they doing now?
Well, one of them is sedimenting and the other one is buoyant.
Yeah.
We're
So
hiding from the one up in the corner.
Sunk to the bottom. And what's the environment they're in? They're still in the space station.
Yeah, they're not free falling.
Yeah, so these guys are no longer in free fall. The whole space station is. the middle of the contraption is, but this is not. So what is it doing? It's accelerating because it's running around the circle. And we're not going to try to answer all these questions, right? So here we see something happening in space exactly the way it would happen on the ground, even though the whole contraption is in free fall. And now the acceleration has nothing to do with gravity. So how do you get the right explanation of what's going on, either on the ground or in space? And it's plain and simple. Some of the guy who just doesn't know. The next one is meniscus. We'll just look at a couple more of these. So meniscus, you know what a meniscus is?
Yep.
You see this little thing at the edge of the water here? So it's like the water is, it gets flat, except right at the edges it goes up a little bit. So what's going to happen in space? So we have this little cell, another one like this, with a camera looking at it. And inside this we have a little Pyrex jar. And inside that it's like half or something full of very pure water. So here's our little Pyrex jar. This is actually from a professor at the University of Toronto who blew this experiment across our vessel. Here's a look at it. Now so this picture is taken on the space station, and you can see that the water is like the two ends of the vessel and a big bubble in the middle. And you kind of see there's a meniscus there, but it's really kind of big. It's like the whole radius.
Is this what you were expecting to see?
Yes. In fact, it's an interesting story about this thing here. This was flown as an experiment on the space shuttle in 1992, but it might have been 95, somebody's in there. A guy at the University of Toronto, professor there, and he had predicted you would, depending on the shape of the vessel, the proportion of air compared to water, he would predict that it would go into this shape rather than hang around on one end or the other. And there was another guy who specializes in fluid stuff in California, supported by NASA, who was their guru on the shape that liquid surfaces take in space. Why would we worry about that? Because if you have fuel in the tank and you want to use it, you have to get it near the exit ports, okay? Where it may or may not be. So you have to design the stuff so the fuel is where you need it, okay? And other things that are liquids. But yeah, so they had this argument going for years and years and years. And so this, what's the guy's name? Forget the guy's name in California. He had a gas can experiment, a little experiment you could put in a space shuttle, kind of in a size of a garbage can, but completely sealed, so you could do whatever you wanted inside there, and NASA wouldn't hassle you about it. He said, I have a gas can experiment. Charles, you fly your experiment because I'm going to prove you wrong. And so Charles flew this experiment, and he saw basically what he was predicting. But he has some problems with his electronics and stuff, and his imaging stuff. So it wasn't really convincing. But Charles predicted this stuff, and he writes all his, like it's an engineering, it's a mechanical engineering problem. He writes all his papers and stuff in journals of physics, physical review. So he predicted it. So we flew this experiment for him again, where he would get much better data. So we did that. And we'll not worry about this. We'll just look at. So here's a picture of it on the same kind of stand. You can see it's kind of a ball in the middle. But now when we rotate this. This is the next one. So here's the experiment sitting on the ground. Don't know what you can, yeah, you can kind of see with the little ball. So he takes it, push. So now the thing is doing what?
Accelerating.
Accelerating towards the center of that circle. Okay? Very simple. And the GoPro picture. So this is the GoPro camera that's kind of mounted to the thing. And that'll be dark. Looks just like on the ground. So the experiment is in free fall, it's in space. But now it behaves exactly like you would see it behave on the ground. So it's got something to do with acceleration. It's got absolutely nothing to do with gravity. Because gravity didn't change. And how much gravity is there in the space station? Just about the same as here. 90% of what it is here. If we didn't have that, we couldn't have a space station in orbit around Earth. And so what happens here has nothing to do with gravity.
Bjarni, when it stops, does it immediately go back to the bubble in the middle, or does it take time?
It takes a little bit of time, but it goes back to the bubble.
So isn't this just Einstein's general relativity?
No, I wouldn't claim that.
We're not going back.
We're just dealing with the simple ideas of physics, you know. Yeah. We'd had to go on like close to the speed of light to get mixed up with Einstein and his funny stuff. Yeah, so it's nothing to do with that. It may have something to do with some of the basic ideas that he was getting at. But,
Yeah, because acceleration and gravity would take on.
so he said there's an equivalence between a gravitational field and acceleration caused by other things. And he's not correct in that statement. Arrogant as I am. And we're not going to worry about that. The point is, like, these are just things that we see here on the ground, and the ideas that people take in basically school, you know. And yet you get confusing ideas out of it. So these experiments are designed to kind of get you to look at this where you can see it behaves. One way if I do this, and another way if I do that. Sometimes it's exactly the same as on the ground, and sometimes not, even though the whole experiment was always done in space. So it just forces you to clean up your thinking about the simple ideas. Anyway, we had a little data unit up there. And so we're trying to just tease out the ideas, and then we build those into curriculum for educators and that. So we are going to be flying more experiments. Let me show you a couple more videos, and then we'll come back to that. So, somebody said balance does not work in space. Who was the brave soul? You'll take credit?
It won't be very reliable.
Okay, it won't be very reliable. They're acknowledging it might work. They're thinking that a balance does not work in space is very common amongst NASA engineers and astronauts. And a lot of physicists who do stuff in this. Okay? And it just points to, maybe we don't quite understand really how a balance works. So we'll look at this video. Do you see what here? There's a space.
And why does it do that while you're trying to search? Yeah.
So here she's got this thing, and this bar can rotate about the center. Got some brass weights on this side, and not on this side. So this is an unbalanced beam. Rotates just like a balance on the ground. Okay? And if we go a little bit further. Here she's getting ready for doing the second part of the experiment. She's muttering something here, but it's just a neat little shot. She's going to let go of this thing. And it just drifts, right? Just drifts nicely at constant speed. Newton's second law or something like that. So now she's got weights on both sides. Pretty simple.
Yeah.
So we hope that we can put these ideas together nicely to better understand how a balance works on the ground. Now, did gravity change between those two experiments?
Nope.
Nope. So balance has nothing to do with gravity. Nothing at all. I can't have one explanation on the ground and a different explanation up in space for the same thing.
Does depend on acceleration.
Depends on acceleration. So this next little one, would a pendulum work in space?
Sure.
Sure.
Pendulum like this.
My brain says no, but the answer should be yes.
It's accelerating.
It will work, but not quite the same as on the ground. And so we had this experiment. We're going to put this little beam in, and the space station is flying in this direction here. And this started off with a beam stationary, pointing in that direction. And we knew that this experiment may get messed up because there's air currents, air being pushed around. And so they may mess up the experiment. What's amazing though, is like this thing did this, what you see here, for 3 hours. Never seemed to slow down, never seemed to speed up. It just kept rotating instead of just doing what we expected, which was rotate, so it would go from being in the direction of travel to being 90 degrees pointing at the. So this one is messed up by the air currents in the space station. And the air currents are there to move air around so that people can breathe and stuff. We're going to fly this experiment again. I'm going to put a cage around it to protect it from the air currents. And then it would take it 84 minutes to go from this to this, which is just about the exact. We're just kind of looking at orbits. There is a little ball, kind of a string, and it's on that little red stand. So what's the ball doing?
Accelerating.
Accelerating. So does it have weight or not?
That's mass.
It has weight right now.
Right now, it has
It has weight.
right now it has weight.
Even in spite of all the world will tell you it's weightless because it's in space.
As soon as it stops moving, it'll stop having weight, more or less.
So what the heck is weight? So this thing's in space, you say it has weight. Whereas everybody else tells you it's weightless because it's in space.
Well, what you're doing is you're changing the conditions because it's not static in the space station that's moving. It's got, was it inertia? Is that the right word? That it's making it go around, which is giving it. It's changing its properties. Yes? No?
No.
Maybe? Okay.
Would it be the transfer of energy from kinetic energy to potential energy?
No,
No?
nothing's happening here, just going around in a circle. Like it slows down because of drag.
Yeah, because also like drag is like kind of like, because in the space station, there's air for the astronauts to breathe. So because of that air, that causes like the spinning object to slow down as a
Yeah,
result
so
of
it causes it to slow down. But let's just focus just on the part, just when it first starts running around in a circle, before it slows down much.
Centrifugal force pulls it up.
It's accelerating.
It's accelerating, and when it's accelerating,
Making a reference to the space station. So it's not, the reference is not the Earth. The reference is the space station.
yeah, so it's accelerating compared to the space station, and we could measure the force in the string when it's doing that. And in fact, this little guy here, this little red guy, has strain gauges in it, and we actually measure the force. And when the thing runs around in 1 second, the acceleration is 1g. Exactly the same as acceleration if I dropped it here. So this is equivalent to the thing just sitting here on the table. We can measure the force on it. When this thing is accelerating compared to the space station, we can measure exactly the same force. In this case, we see it's accelerating. But mostly we would probably think that when it's sitting on a table here, it's not. We gotta measure the same force.
It is, because gravity is exerting a force on it.
But gravity is, whatever gravity is doing, it's doing the same to this thing when it's running around the circle as when it's stationary. So you can't blame it on gravity. Gravity is blamed for a lot of stuff that is completely innocent.
Is this the solution that I forgot the name of the space station, that the station needs to move so that the astronomer don't have the sickness when they come back to Earth due to lack of gravity?
No. When you come back from space, you've gotten used to not using your muscles in your legs. And you've taught yourself to ignore the signals from your vestibular system. And then you come back on the Earth, and now you got to stand up, which means you have to use the muscles in your legs. And you use the signal from your vestibular system to figure out which way you're pointing. Okay? And so you've lost that. And so for the first few hours, you have to be very careful moving around as you get your balance back and you get your muscles working correctly.
But they are saying, for example, I forgot his name, Kelly, that stayed for 1 year,
Mhm.
had like swollen legs and stuff, and people were saying if you create like a rotation, kind of artificial gravity, you put the muscle to work, and that can alleviate some of the
See,
symptoms.
so when we're standing here on the ground, what's the blood in my body and the fluids in my body trying to do?
Go down.
Go down. And so something stops it from going too much. My muscles working. My muscles are like a pump. My heart is a pump. And so it's pumping the stuff back up, but it's always trying to flow back down. You go into space, and it doesn't flow down to your legs. But the pump, your heart and your muscles are still working. So it's pumping it up. So that the fluids in your legs are pumped up to your chest and into your head. And so the first few days that you're in space, you feel like you have a head cold. You have a stuffed head because the fluids have shifted upwards, you know. When you come, so, and then what happens is your sensors in your chest sense there's too much blood and fluids in my body, and you dump it out, you pee it out. So now when you're in space, you have less total fluids in your body. When you come back to the ground, well, now that less fluid wants to go down here, so now I got too little up here. So now I have a problem. So before you come back, you drink 2 quarts, like within 20 minutes of coming back, you drink 2 quarts of salty water. Yeah, salty
The
water.
electrolytes
So
back.
I like to drink salty chicken soup, because I didn't like salty water. But not like seawater, that's different kind of stuff. And so you load yourself with water, and it's salt, so it goes into your body.
Maybe like a
Just pure water.
Gatorade or something?
Sorry?
Like a Gatorade or something like that?
Well, Gatorade is
Or
sweet. It's got to be salt.
Without sugar.
Yeah. So that replenishes your water supply. So now when you come back, water goes down to the legs again. I haven't depleted myself out here.
What do you mean salt?
Because otherwise your body won't absorb normal water, just pure water. You have to dissolve it. So your body absorbs the water.
But if the station were rotating, you do not create like artificial gravity that
That's a good idea. So we can rotate the station to create artificial gravity. Do you know how much we spent to build the station? To be able to do stuff in free floating? $100 billion. And you want to spend another $50 billion putting it back. I might as well just stay here. So, like, you can do that, but it doesn't make sense. It's like completely contradictory to what we're trying to do. Now, if you build big outposts out there someplace like the L5 Society, and people are going to live there, yeah, then you can spin them around so they can walk around the outside of their craft. But with a space station, we're trying to be in free fall. So you can't, so it doesn't work. Anyway, so we're going to be flying more experiments of this type, and they're all designed to sort of look at simple ideas, but do it in such a way that it, like all of this, you look at this here, and you look at that there, and the same thing's going on, you end up with a conflict up here on just simple ideas. So this is designed, let's explain these things correctly, so you don't have the incorrect ideas of what's going on. So the other thing I was thinking of doing was flying a little telescope as one of the experiments. And I could, like if I tell NASA I want to put a telescope in the space station, they just say, which flight do you want to be on? Right? But then you start looking at the logistics of trying to do that. Okay? And there's so much bureaucracy on top of this thing, the logistics of getting it up there. And the telescope, we really wanted to be outside, not looking through that window. And looking through that window, that would really mess up the telescope.
Yeah.
And you want to be outside, which is possible, more complicated. But I tell you, if I tell NASA I want to do it, they'll say, when do you want to go? Yeah. But it means that the hardware is going to be more expensive to build. It's going to be a lot more complicated to operate because now it's outside. So those astronauts can't deal with it. which considering how the one guy messed up my experiment, was not a bad thing, you know? We could operate it from the ground. We could, like the space station goes around the world 16 times a day. It'll pass over, say, some part of Canada, at least every day. One or two passes someplace. So we could send stuff up directly to our little gizmo up there, which I wish we want to point it. The station, when it's going, so this is the front of the station, when it's going around the Earth, it always points in the same direction compared to its flight path. So it's always, this part is always pointing towards the ground. So now I got to deal with the station's doing this, so now I got to point my telescope. So it winds up 360 degrees every 90 minutes, so I got to unwind it. Well, maybe I have to look off to the side, but now my telescope is doing this. Okay? So it just gets really complicated. And then I got all these appendages, solar arrays, radiators, antennas and crap to look at. Yeah, so we were thinking about putting a telescope in space. And then I got a call from these guys in Ireland who want to do some of this kind of stuff in space. And they had some ideas about doing it, and I went over there and they asked me to come over, and I went over there and chatted about some of these. Because people have a lot of funny ideas about what space is about. We found some of them today, no offense. So they have a lot of misconceptions about the space stuff. And so what they were going to do didn't make much sense. So I suggested, hey, let's put a telescope in space. And it would be for amateur astronomers and lay public and some research stuff, give lots of people access to it. And so that's kind of what we're working on. We're not there yet. So part of what is driving it in Ireland is they want to use this to help bootstrap Ireland into doing stuff in space. It's a huge money predicted to be made around or spent on space stuff. And what we want to try to do is kind of copy Musk in building he built low-cost, reusable rockets, and it was the low cost was the more important thing. Musk and SpaceX, they developed the Falcon 1 rocket, the Falcon 9 rocket, and the Dragon capsule for $600 million. That sounds like low cost?
Relatively speaking.
If NASA did the same thing, it would be $6 billion. Hands down. Okay. So he has just got a streamlined way of doing stuff, in part because he makes use of a lot of old technologies that NASA developed back in the 60s and 70s. And so we're looking at with an optical telescope that people have access to with a 25-inch mirror. Like I do the techie part of that. Their job is the harder part is to get all the money in this. And then give people access to this where you can control it from your cell phone, get your images down. And you get pretty much complete coverage of the sky. You're not limited day and night, or night only. No moonlight scatter, no atmospheric distortion, no weather issues, no light attenuation.
Never cloudy.
Never cloudy.
So how would you get past those obstacles of, the telescope being pointed 360 degrees?
No, that's what the space station does.
Right.
Telescope doesn't have to do that. Like if I point this telescope, say, at some star, okay, and I have it stationary there, it's going to orbit always pointing exactly at that star.
As the Hubble does.
That's a Hubble does.
Okay, so it would be free floating, free standing?
Well, it would be, yeah, essentially if you could point it and leave it perfectly still, in terms of rotations, it's going at 17,000 miles an hour like this.
Right.
But if you got it so you had no rotations when you stop messing with it, it would stay pointed perfectly at that star. Okay? That's unrealistic. So we actually would have a guidance on it, and it would lock onto the star. And just very low level thrusters always keep yourself pointed at the star.
So this would not be attached to the station at all?
It have nothing to do with station.
Okay, all right.
And then we still set up things where we can communicate with it from home.
A mini Hubble.
It's a baby Hubble.
So if your research group launched one of these, and then say somebody, I don't know, Sweden or Russia or whatever, wanted to do the same thing, if enough of them got up there, who would be responsible, or what would be, if two of them actually hit one another because you're doing your own thing?
You're kind of a mess, eh?
Like I'm just saying, like, I mean, airports, they have these people to tell everybody what to do.
Yes.
There's someone in charge.
Yes. And so for space stuff, there's about 30,000 things in orbit around the Earth right now. It's a lot of stuff. Everything bigger than this bottle here is tracked on a daily basis with radars from the ground. And tracking it just for a few minutes, I can predict where it goes for the next 3 to 4 days. Because the orbits are very well defined. And I can tell you, because they track like 10,000 of these things, they don't track the stuff that is smaller than an orange. There's about 10,000 of that they track on a daily basis, and the U.S. Air Force does this, and they make that data available to everybody. Russia, China, Iraq, Pakistan, Iran, everybody. Because they don't want their stuff hitting their stuff. The other guys hitting your stuff. So that's tracked on a daily basis, and so they predict ahead collisions. And so the space station has to be maneuvered a little bit, change its orbit a little bit, about 3 times a year to avoid being hit by something. The number of times you've had collisions in the last 60 years, there's been 1 collision in 60 years. And that was a dead Russian satellite hit an Iridium satellite and made a huge mess. So the probability is really, really low as you're hitting something. But you track these things to avoid collisions. And then when you do these things now, when you put stuff in orbit around the Earth in what's called low Earth orbit, anything below 1,000 kilometers, you have to show how your spacecraft will be out of orbit within 25 years. So you have to design it so it comes out of orbit. It will ultimately come out of orbit. And from 1,000 kilometers, it'll take, well, it would take about 25 years. It will be out of orbit. So they mount the stuff up there. Hopefully, reaches kind of space.
So when they launch a rocket, they are so sure about the trajectory, so it doesn't.
Yeah. Yeah, I said, so when you launch a rocket, you're so sure about the trajectory that you know you're not going to hit anything. What if the rocket has a mind of its own and it goes someplace a little different? All the rockets have explosives on them, and there's a guy called the range control officer, and if you go off your path, he pushes a button and blows you up. You're not going to get to space, even if there's people on it. So the space shuttle, there's a range control officer, and if the space shuttle was to wander off the path, he pushes the button, blows you up.
Even if you are way up close to your destination?
No, once you get way up close, then you can't be far off your path.
Oh.
You wouldn't get way up really close if you were off your path. Okay, so you do a path control towards the end of your launch. So if before that you were off the path, you get blown up.
I was watching some videos that the Russians, they didn't have this system, and sometimes if the rockets go crazy, they will just leave it to do whatever.
No, I think they blow. I think this is like it's an international treaty now that says you have to, everything you put up there, you have to show how you're not going to have that kind of a problem. and all the countries have signed up. Anyway, so the idea of this thing here is the thermal stresses. So that's a critical part of the component, the thermal design of the spacecraft. And the mirror, you have to control the temperature of the mirror to about 0.1 degrees everywhere on the mirror, so the mirror is not distorted more than 20th of the wavelength of light. So that's one of the critical in all spacecraft, not just the telescope. So the student did, like showed them how to do this stuff, and had them do this kind of thermal analysis. And the other part is the stress analysis. Now, when you're in space, how much stress is there? None. You're just freely falling. But you have to go up in a rocket.
That's
The
lots of
rocket
stress.
gives you 3 or 4 G's acceleration, and a huge amount of vibration. Because you have to design it to survive the launch, and then design the thermal stuff so it can operate successfully in space. And so the students worked on these components. And this is some of the dynamics of the fleet that supports the mirror. And then all these nice little graphs that show the frequencies of vibration and stuff. And a bunch of mathematics in order to do all this stuff. So basically, they came out with the estimates that I had made on sizes and masses and stuff like that were pretty good. And then now we have a better idea of that. And so the next step would be this series of what the telescope is going to do. Anyway, so the idea of this is to try to put this kind of thing together. And the offices that we have now are at the University of Limerick in Ireland, in this building right here. And they have some plans of building fancy buildings and things over there. Nice little sort of a, kind of like the accelerator center up north of the University of Waterloo. So it's up over there in Ireland. And up there in Iceland is where the design of this is done. If we pull this off, the actual design of the telescopes will be done here in Canada, because I know all the right people here. Some of the build would be in Ireland, but some of the build would be here too. So that's kind of the plan. So now this is totally shift topic. So who's this guy?
Neil Armstrong.
What's older?
Apollo 15.
The moon buggy, so it has to be 15, 16, or 17.
Yeah. And the moon buggy is here. I think this is John Young. There's nobody else. Right? Anybody know John Young?
First pilot of the shuttle.
First pilot of the shuttle. He flew twice on Gemini spacecraft, twice on Apollo. We flew Apollo 10 around the moon and back. And then I think it's Apollo 15 or something. And then he did 2 shuttle flights. Yeah. I shared an office with him. I flew in a T-38 with him a few years back from Houston to San Francisco. We did practice short field landings on the space shuttle simulator, and then back to Houston. Hey, that's 50 years ago. And NASA's been thinking about, always kind of puttering with, we should go back to the moon. Some people are talking about go to Mars, go to asteroids, whatever. And these are some pictures that were NASA people putting together ways of getting back to the moon. There's a new game in town. What's the new game?
Blue Origin.
That's one of them, yeah.
SpaceX.
SpaceX. Blue Origin there as well.
And
And then things like this is White Knight and Spaceship One, which is this guy here. Bert Rutan built this. What's neat about this is he didn't just build an aircraft and a spacecraft. And for very low dollars. They spent $25 million building this. Boeing would take $250 million at least. But he made it look so intriguing. Just to rub it in people's faces. He can not only build it so it works, he can make it artistic and intriguing as well. And so the spaceship one flew twice into space, above 100 kilometers and back down within 2 weeks. And they won $10 million. And it cost them $25 million to win.
It's pretty good.
And then Virgin Galactic picked it up, so this is the current one that is being worked on. This is Spaceship 2, White Flight 2. A little bigger, you can buy a ticket to go for a ride. You go into space, 100 kilometers, and then back down. You have about 4 minutes of free time. Total ride is about an hour. The ticket, a measly $250,000 US.
Non-refundable.
Non-refundable, yeah.
Start buying
Yeah,
lottery
so-
tickets.
So this has flown, it hasn't taken any passengers up yet. The first version of Spaceship 2 crashed. One guy was killed. It crashed because of a pilot boo-boo. Yeah, the guy did something when he shouldn't have done. So Spaceship 2 is flying now in test mode, and they're getting closer to taking these paying passengers. The first paying passenger was supposed to go in 1992. A little bit late, so they're getting there. So this was the second version. This is from January this year, the first rocket flight of this thing. At the same time, I don't remember all of these things here. Boeing is building a thing called the Starliner, kind of an Apollo-looking capsule, and they're getting ready to fly people in this. And so people are training to fly in it. And I trained with Sonny Williams and Ken Ham. No, they're going to fly in this thing. I'm stuck here watching it. And so that's going to fly with people in it probably within the next year or two. And then NASA is building Orion, which is a slightly bigger Apollo-looking thing. And it's designed to be able to take people to the moon and back and keep you in space for about 30 days. This program here, SLS is a space launch system, a big rocket like the Apollo 5. Or was it Apollo 5? Or Saturn 5. Saturn 5. This program, $18 billion. And about 15 years. They're planning to send the first one of those around the moon, no people on it, around the moon next year. So they're going to go around the moon, circle a couple times and come back. And then a couple of years later, put a crew on it, around the moon and come back. And the game changer, Elon Musk and his gang, they built. So here's a little person. Not a little person, a normal sized person. This is Falcon 1. This is Falcon 9, which is the one they're using a lot now. And this is Falcon 9 Heavy. This is the one that he launched his sports car in. The Tesla, red Tesla sports car, which is someplace out in space. Huh?
Cruising.
So these ones here,
Playing the beach.
and the Dragon capsule were developed for $600 million. So that's the Dragon cargo ship, Dragon 1. And it has done, here's the Tesla. This is the actual picture of the Tesla after it was launched on the top. That's a real car.
Did they?
Good that it's an electric car because there's no fuel on it.
It was a used car, it was his old one.
Yeah, it was his old one. Anyway, so here's the Dragon 1. It's done about 17 flights to the ISS. The last one was just a couple of weeks ago. We had some of our stuff on it. And then there's Dragon 2, which is man-rated. So this one has its own little rocket, so that in case during the launch if something goes wrong, pull the astronauts away from the blowing up rocket. And it was launched to the space station, first one just this February. Did about a 5 or 6 day flight. And they were going to launched people on it in July this year. What? You know, so first flight to the space station went okay, March 6th this year. In April, they did a flight test of the crew escape system, and something happened. They're actually testing something about the engines on the launch pad, and something didn't go right, and they got enveloped in orange smoke. And we haven't heard what happened, but it wasn't very good for the capsule. And they also did a test of the parachutes that actually bring it down. They were purposely, and they had kind of a dummy capsule. They were purposely failed one of the 4 parachutes. The other 3 should have brought it down safely, but they didn't open properly when the 4th one failed. So it went plunk into the desert, would not have been healthy for a crew. So they're still trying to understand those things. So the first flight was supposed that people were supposed to be in just a couple of months, but that's postponed until they understand these problems. This is not a bad thing. This is a normal thing in spacey stuff. It's not easy to do this stuff. And, you know, so you learn from these mistakes and do it a little better, a little better. And things are working really quite well overall these days. There's very few launch failures, very few launch failures. Anyhow, so here's that little man. Falcon 1, Falcon 9, Falcon 9 Heavy. This is what he's building now.
The BFR.
Yeah, this is massive rocket. Will it happen? I don't know. It's, they don't say much about what they're cooking up until kind of, hey, we're going to launch it. Like those rockets that come back and land. So amazing. So there's a picture of that one attached to the space station, and it's like 3 times the size of the space shuttle. It can take 40 people into space. Now, are they really going to build this? Don't know. I think they're working on maybe something a little less ambitious, maybe a little smaller, but they will do something like this. Just don't quite know what. And they're going to send down around the moon, and actually they sold the first tickets. Japanese billionaire take himself and a bunch of his buddies to fly around the moon in about 4 years. What's that ticket worth?
2 mil,
300 million.
300 mil.
Pretty well pays for the development.
That's the idea. That's how you keep your business in business. And I think this is a good chance of happening. Elon Musk needs to do a lot of what he claims he's going to do. Then they're going to take this BFR and they want to land it on the moon. And you know, when I saw the first time they brought that thing back and landed it on the pad, you know, why are they doing that? It's actually not so cost effective to do that. And I was at a conference a year and a bit ago, and Elon Musk was there as the lunch speaker, and he said they're not saving any money doing that, at least not a year and a half ago. Maybe they'll get to the point that it saves a little bit of money, and when you do that, it takes a big chunk of your payload out, because that stuff weighs extra. You have to carry extra fuel, and those feet that come out that weigh stuff, you lose it off your payload, so the cost of your payload goes up. But that technology, and they've done about 30 landings so far, and it just like works. Okay? That technology is what is needed to land this guy on the moon. That's the driver behind why they're doing it.
Rogers, that's what it is.
Yeah, and they're going to do this. So this is their picture of what they want to do on the moon.
It looks like a picture from a 1950s science fiction novel, doesn't it?
Bugs Bunny sitting on top.
They're developing a new engine for this stuff, and they completed the test of that sometime earlier this year. So they've got their new rocket engine working, and then you can set this like the booster here can come back and land like they're doing. But this has its own. This is its own second stage. It gets you into orbit. You can send one of these up as your fuel truck, connect the two, transfer the fuel into it, and it has the fuel to go to Mars and back. So it can land on Mars. And they have this great idea of doing stuff on Mars.
spaceport.
Yeah, so.
Are us gray hairs gonna see this? Probably not. Some of the younger people, maybe. But there's, like, it's easy to talk about doing this stuff, but going to Mars takes 6 months to get there, and there's no shortcut. You can't come home until 18 months later. It takes you 6 months to come back. So it's a 2.5 year journey. There's nothing waiting for you. No people, no fuel, no food, no whatever. There's a huge amount of infrastructure that has to be developed and put in place before people actually can go there. You might be able to send somebody in this thing, go around Mars, look at it, and come back. It'll be a 2.5 year journey. Nobody's been in space for more than about 1.5 years. The longest is a Russian, about 20 years ago. Stuff doesn't not break. The space station is made to be fixable. So we don't have the capability yet of having something last for that 2.5 years without having a lot of redundancy and looking at all the failure mode, et cetera. So it's a little ways off. And this here's a long ways off. Anyhow, so I came across this, I don't know when, 25 years ago, from Socrates from 400 BC. Man must rise above the atmosphere and beyond, fully understand the world in which he lives. I have no idea what Socrates had in his mind. When you look at the stuff we've got going on here and the things that are happening in the world, we get so much information about it from space, looking back at it, looking out there, that this really is absolutely true statement. This is one of my favorite pictures. Maybe you recognize this little country? It's kind of fuzzy looking.
Looks kind of Iceland-like.
Kind of Iceland-like. So Reykjavik is right here, my grandmother and grandparents lived here, and my father's parents lived up here. I was born right there. So it's been 60 years since I left Iceland, but I've seen more of Iceland than any Iceland. Anyhow, so that's my little story. I'm happy to answer questions if you have energy left.
So when you fly to Mars, are you still in the free fall or what state? There is any gravity or something? Just acceleration or?
Okay, first of all, you never get away from gravity. Okay? Idea of gravity, free fall are different things. So you always have gravity, Earth, Moon, Mars, Sun, whatever. But you're always in a state of free fall on your way. Free fall just means you're accelerating freely with whatever the gravitational acceleration happens to be where you are. And when you're in that state, then you float inside your spacecraft. And so I would take this model here, and I just throw it up in the air. Between the time it left my hand and hit my hand, it's in free fall. And nothing to do with gravity. Okay? And all the pressures and stresses just disappear. And if you throw it high enough so that the water's got time to settle, it would do exactly the same thing as we saw there. It's just that it takes a little longer to do that. Yeah, so you'd always be in free fall.
When SpaceX really got started, a couple of astronauts said, came out, and it's really hurtful to Elon Musk when he said this, that they said that private enterprise shouldn't be involved in space. And just curious, like, what is that? Just the NASA way? Is that just because they were brought up in? Just curious if you had what you thought about that.
I think that's an example of we all tend to get stuck looking at things and thinking about things the way they happen to see them. It's really hard for any of us to break out of it. And like some of these ideas we talked about, the science stuff, you guys have a lot of ideas in your mind, and you just show maybe they're not quite right. So you get stuck in that. And it's so expensive. The way NASA, Canadian Space Agency, ESA does stuff is so expensive that companies couldn't afford to do it because companies have to make their money back. So Elon Musk cut the cost by a factor of 10. All of a sudden, it's not so expensive. So So it used to be, you think of the launch cost is $20,000 per kilogram. He's got it down to, and all the new stuff people are building isn't bringing the price down, taking it up, except for Elon Musk. He's down to $3,000 a kilogram. Now you have to send big stuff up to get, which is space, Falcon 9. So as soon as that locked mind saw this, they started saying, oh, we can actually do a lot of stuff if you just do it efficiently. NASA is still in a quandary. Canadian Space Agency is absolutely lost. But NASA is still in a quandary, like how do we deal with this, you know? And so now they're talking about, instead of finishing their big rocket, just buy the rocket from SpaceX. They've got the rocket. Just put your stuff on it. So that means the Boeings and the Lockheed Martins that developed this for $6 billion for the rocket can no longer have that kind of business. So now Boeing and the companies in Europe, Aerospace, now they're working hard to make lower cost rockets because they're going to go out of business if they don't. Competition factor. And I think we're not at the end of where we can go. And part of what we're trying to do here is, like if you had the Canadian Space Agency develop this kind of little satellite, you're talking a $50 million bill. It doesn't have to be that expensive. Like we know how to do all this stuff, just you need a small team of guys that know what they're doing, instead of a big team of guys that don't know. The rest of it. And Elon Musk has just said it can be done. And he's just showing.
I have a question about the how does the airlock?
Speak taller.
Okay. How does the airlock on the ISS?
How does the airlock work?
Yeah.
Yeah, so you have the main module of the ISS.
Yeah.
You have another little module attached to it. There's a door in between them. Okay, there's a door on the outside of the little module. Okay, you can open the inside door, go to the airlock, close the inside door, test it, make sure the pressure's okay so you don't take the air out of the space station, open the outside door, then reverse it.
How is it automated?
That part is not so much automated. No, that's serious. And the space station is not automated. That's right. There's people on the ground are watching everything. The astronauts don't make a single decision out there. They just do what they've been trained to do, and anytime they do something, there's people on the ground that are getting huge amounts of data on what's happening, much more data than the astronauts have time to look at. Because there's 300 people on the ground watching space station operations.
Don't you have HAL 2000?
There's no HAL 2000. Not yet.
Aren't they glad?
So going back to the experiments and considering your years of experience, other than the wrongly executed spectrometer experiment, was there ever a case where you collected data and what you hypothesized and what came back were considerable? Was there ever a case where you were shocked?
No, the only thing that surprised me was that pendulum was continually rotating. I wasn't surprised that it didn't do just what I expected because I knew air currents were there, and we just didn't have the time to build a strong. The fact that it just continued to rotate for 3 hours, what's going on? That was a surprise.
Because of constant air circulation?
Yeah, it could be that there's a pattern to the air currents, so that if there's an arm here and an arm there, maybe the flow is a little bit more here than here, and so this just keeps pushing it. You know, it takes about 1 minute to rotate, and by the time it's gone this way, then this one is pushed. So it's just an air current that just keeps driving. So that's what's happening. But no, I would say no, there were no surprises in this. And there's a lot of analysis goes into all this, and none of it is build it and see if it works. It's all everything is analyzed, and I could show you some god-awful equations that goes into this. That shows how it's all going to be.
Without air currents in the space station, could the astronauts suffocate from their own CO2?
Yes. And they would. If, you, if you're not circulating the air, yeah, you're going to suffocate.
Isn't it noisy in the air in the space station as it sounds?
Yeah. Yeah, there's also fans going. There's fans that are moving the air around. In every experiment rack, there's fans that are circulating stuff, circulating fluids, transferring heat and stuff, so it's noisy. But it's, I don't think it's terrible.
Getting back to the, I guess, the very beginning of your presentation, you're talking about getting stories and things, promoting STEM and so on. What's going to come to the teachers in the classroom here to...
We have curriculum that we developed some of it, we're still working on some, but we have actual lesson plans and curriculum, and then comparable experiment hardware.
Okay, and how are you going to get past the politicians that are deciding that what the curriculum is going to be, and that there shouldn't be science, or there shouldn't be music, or there shouldn't be this, that, and the other? How are you going to get past that?
I wish I knew the answer to that, because you know, we started this a few years back thinking, okay, we can do this kind of stuff, and well, I'm not so sure we can. This, especially down in the States, it's mind-boggling what's happening down there.
And we've got our own here in Ontario.
Well, come down in a second. So, like in the States, they've come up with these new generation science standards, which are developed federally, I guess, and trying to get them across all the states. Okay, the smart states will stay the hell away from them. It is the worst example of how to try to teach science I've ever seen. Trying to teach it at too low a grade level, teaching an idea in grade 1 about pushes and pulls and Newton's laws, and then nothing on that until 3 years later, and then nothing until 3 years later. You know, who the hell?
Cold storage.
It's just like, it's bizarre, it's so bad. Can you get them away from that? Well, they've spent tens of millions of dollars developing that, so who knows? You know? So that's a big problem. Now, what Ford is doing here, and I'm not a fan of Ford, but what they're doing in education, I don't know all of it, but everything I've heard, I agree with.
Really?
The problem with education, like this whole thing of discovery learning, it's like nonsense, absolute nonsense. You think about, like what did it take to discover the stuff we know now? Like even simple science, like just Newton's law said. It took 2,000 years for the smartest guys in society, little by little, figuring this out to get to where we are now. And do you expect kids from grade 1 to grade 12 to get there on their own?
You expect politicians that know nothing about science to be able to promote this. Uh-oh.
Nice.
Uh-oh.
And yeah, so, like I don't know who, but going back to the basics, reading, writing, arithmetic, kids are coming out of school now without being able to add and multiply and subtract.
I can't read.
Yeah, the kids
Yeah.
don't. They can't.
Yeah, get back to that. Get rid of the trying to teach higher level stuff in grade school.
Exactly.
Teach them the basics. That's what they need. Because like I've got a buddy here that is a high school teacher in the system here. He's teaching math in grade 10. Yeah, math in grade 10. His kids can't add or subtract. How the hell are you going to do math if you can't add or subtract?
Fingers.
Like, it's just like, you know. And he's like frustrated. And he was educated in Nigeria. That's where he came from. And he's baffled by the quality of what is going on in the schools here today.
So, do you think Obama should have kept the shuttle program going until they had a replacement? And if we had the shuttle program still running until now, would we have been more advanced in, say, building more of the ISS, or even having another mission to Hubble?
Yeah, and this is like, I won't claim to have all sorts of insight on this. But I think the shuttle should have been kept on. There's nothing in the works that can do the job the shuttle does. It can take 50,000 pounds up and bring 30,000 pounds back.
Yep.
Nothing else can do that. The problem with the shuttle is it costs a lot of money.
Building a lot.
Why well, they say $500 million on launch. Why did it cost that? I've been in the shuttle hangars a lot, but people are doing stuff, and I tell you, for every person that's working, doing something on the shuttle, there are 5 people watching. And the cost, the only thing you pay for, anywhere you're buying anything, the only thing you ultimately pay for is for somebody's time. You know? That's all you pay for. This bottle, it's not worth anything. I paid for the time it took to make all this stuff and to get the water and stuff it in here and drive it to the store and stuff like that. So you pay for people's time. So if you had a small workforce, 2 people instead of the 5, the cost of the shuttle launch would have come down to $150 million. And there's nothing that would take the same payload to space and back with the shuttle for that kind of cost. It's an incredibly inefficient way of operating. And that's what Elon Musk has gotten to do. Is what he's doing with a much smaller. Now, a lot of the people that work for him are ex-NASA people. People that know what they're doing, and then they have a lot of young engineers that have good guidance from those people that really know what they're doing, and they come up with new ways of doing stuff. So, yeah, I think it should have been kept for a lot longer, and you get past these issues.
Commercial applications, you know, we did hear, I think years ago, about things like ultra-pure pharmaceuticals, things like that. The crystals could be grown in free fall. And are you aware of any low Earth orbit commercial aspects that haven't been touted much?
There's very little that I'm aware of, but again, I haven't been tracking this stuff. Okay, but you know, the cost of getting stuff to the space station and the cost of operating up there is so high. And the whole thing of commercial operation, I think, is a pipe dream.
Yeah.
It doesn't mean you couldn't get the cost down, but you have to change how the heck you operate. So there is a commercial venture going on now that is actually developing a module like the space station module. It's going to be attached to your space station sometime in the next few years, and then detached. And if they streamline the operation of that, maybe they can get that. So that's one of the problems, I guess. The other real problem is NASA was so anxious for somebody to win a Nobel Prize for doing something on the space station that they never let the science community do the fundamental things to figure out how to do stuff how to do stuff in the space station. So none of the really basic science that you would do in any lab in the university here, before you start doing an application, that's never been allowed to happen. It wasn't politically acceptable to do it that way. So the science community is not big on space station, by and large, because they have never been allowed to just do the proper science and build up the capability. And that is so incredibly hard to do stuff like putting a telescope on that. Man, that is such a burden to try to do that.
You brought to our attention that there seems to be a Russian half of the space station and then the rest of the world.
Yeah.
What is the proportion of basic research that happens in the Russian world compared to the international?
I really don't know. I really don't know. I know not all what goes on the ISS side, and I know nothing of what's going on the Russian side.
Is the lack of atmosphere on the moon an issue to colonize because you are exposed to meteorites and
Yeah, it's going to make it kind of expensive, and you have to have good spacesuits, and you have to have all your living quarters have to be protected from radiation and all sorts of stuff there. But I think the moon is only 3 days away. So as much as you go to the moon, you can stay there for a couple of weeks and come back over a 2-week or 3-week period. So those problems, challenges are a lot easier to handle than with Mars. And Mars is long.
also speaking to Mars, because the flight is so long, yeah, 6 months. All the problems with long flight in free fall are solved. I mentioned the issue Kelly had with.
A lot of the problems were the people in free fall for long duration. A lot of them are obvious. So everybody has to exercise for 2 hours every day on the space station. And that's to keep stresses in your bones, to reduce the bone loss, and eat a high calcium diet and some other stuff. So a lot of those problems, really, people have a pretty good handle on it, and they're learning more stuff. You know, I go down to NASA every year for my medical, and they do more stuff on me than they ever did before. Like I had really, really amazing scan of my eyeballs in February. Pictures of the layers in my retina and all sorts of neat stuff. And they're learning like some of this changes in space when your pressure is still in your eyes, but yeah. So they're doing a lot of stuff, and they are learning a lot of stuff. So they're making progress.
Well, last question.
You mentioned the shielding that may be needed to go to Mars or even go to the moon or anything like that. Does NASA have any type of, say, low-density shielding, or is most likely shielding going to be water?
Most likely it'll be water or fuel. Yeah. But you know, like people make a lot about the radiation stuff, and I go, you know, my chances of dying from radiation compared to dying from my spacecraft exploding or other bad things happening, like one is like a real risk. The other one is I have a 3% higher chance of getting cancer sometime in my life. Like, I'm not worried about it. And I guess it is greatly overblown. That's the. It's the bigger immediate risk that we really have to stop quitting so you don't have oxygen. Yeah, thank you for your question.
All right, we're pretty much running a full program time-wise, so I think we're probably going to bring to a close. I don't know if there's any last-minute announcements or anything we need to know about. Jim, anything?
Check the Facebook page. There's a kids science thing at Western University tomorrow. And Ellen, you put a link of Blue Horizon or Origin? Yeah, okay, on the Facebook page. So, and who's here for the first time? Ooh, you're guilty. Before you leave, make sure you get a card from us. It's got all our contact information. And we have another meeting 2 weeks from now down at Zares. And we're doing, well, we won't have an astronaut, so let's just scrape by.
Excellent. Okay.
There's the.
Now, just before we go, everyone is welcome to join us. We typically go to the Hooters lounge down the road for a beverage and a snack. People are welcome to come along with us down there. So we'll be down pretty much as low as you can go in Hooters basement.